The last time we met, we were talking about the concept of alleles. We're going to finish that up today, talking about a little bit more agarose gel electrophoresis. At the end of that topic, we're done with exam 2 material, and we're going to do a little bit more after that today. Last time we were here, we were talking about these two fragments of DNA, two homologous chromosomes, chromosome 1 paternal, 1 maternal, and there was an enzyme called SMA1 that recognizes that palindrome, CCC-GGG. If I was really useful, I would label the polarities for you, like that. And that enzyme then would cut the paternal version of the chromosome. That enzyme cuts the backbone in between the C's and G's. This particular enzyme does. But it won't do that in the maternal version because that same recognition sequence on the maternal homolog is not CCC-GGG. It's not a palindrome because there's been a C to G mutation. Okay. So what I tasked you to do last time was to load those DNA samples on this gel, pretend like you load them on the gel. In the absence of enzyme, that is without trying to digest those two pieces of DNA, and then on the right side with that restriction enzyme. So how do we know where those bands are going to show up, band or bands? What's the size of the DNA fragment without cutting? No enzyme, there won't be any digest of that piece of DNA. So how long was that piece of DNA in base pairs?
18.
It was 18? Okay. So where would we draw that band?
Right below the 20.
Yeah, right. It's between 18 or 10 and 20 base pairs. So there should be a single band like that. If you don't provide enzyme, then the paternal version won't get cut by SMA1 if there's no SMA1 enzyme present. So both the maternal and the paternal versions of that DNA sequence, paternal chromosome, maternal chromosome, both of those are 18 nucleotides. So I'm just drawing the double helix as a single black horizontal line. So that's without enzyme. When we add enzyme, SMA1, it's going to cut in half that paternal chromosome. That's going to be 9 nucleotides each fragment. That's only because I designed the chromosome to have the small one side exactly in the middle. If it was anywhere else, you'd have to figure out how many nucleotides were on the left side of the cut and the right side of the cut. In this case, it's even, 9 and 9. What happens on the right side when we've added the enzyme to this PCR mixture? What happens to the maternal copy? Does it get cut or not cut?
No.
Why no?
Because it doesn't have the sequence.
It does not have a SMA1 restriction site, so it doesn't get cut. So when you load these on the gel on the right in lane 1 and electrophoresis it, separate all the DNA fragments in this whole mixture by size, load that in lane 1, what's it going to look like? How many bands are there and where are they located? How long is the uncut fragment?
18.
Right, so there's still some DNA fragments in there that are the maternal homologs, they don't get cut, so you still get a band at 18.
And
That comes from that molecule of DNA.
won't there be 2 times as many in the 9 category? Because same amount of DNA of each, but one gets cut in half.
Right, so you get a band at 9, and it may or may not be twice as dark or twice as bright because there are twice as many molecules of DNA. For every 1 molecule of maternal chromosome that shows up at 18 base pairs, there are twice as many that are the size of 9. So there's more DNA in that part of the gel, in other words.
On the exam, will you be like paying attention to how thick the...
Absolutely not. Good question, but so thank you for asking. I won't be paying attention to how dark or light or thick or thin the bands are if you do one of these sorts of problems, because it's hard for me to quantitate your drawings. So as always, artistic merit of the drawings is never going to be a part of the grading rubric. One, because I'm not an art critic, so I don't know how to judge art anyway. And second, it's a science class. There is some art to science, but not usually in the way it's drawn. What, just by chance, let's say that SMA site had been off the center of the paternal chromosome just a little bit, so that it was making 12 and 6 nucleotides. Use a different color, say green. There'd be a band at 12, and there'd be a band at 6. They wouldn't be twice as dark because they're different sizes. They're not all the same size. They're not piling up in the same part of the gel. So again, the point is, the reason about the question about why that band might be twice as dark is because there are for every one molecule of that chromosome, there would be 2 fragments that are 9 long, twice as much DNA, that exact size. If the DNA fragments are different sizes, then you don't get that same effect. Any questions or concerns? And I just wanted to show you an example of an actual RFLP gel, restriction fragment length polymorphism. Last class we talked about AFLPs, amplified fragment length polymorphisms. These ones are called R for restriction because it requires a restriction enzyme, one of these enzymes that cuts a piece of DNA, to make that change in size of fragments obvious. So briefly, this gel is organized, at the top here are the names of different sources of DNA, different worm strains. The naming's not important. 5 different worm strains, numbered 129 through 133, and then a couple of other worm strains, AF16 and HK104. So they all have DNA, and the primers I'm using here create a single-sized band, which is whatever size that is based on whatever the unlabeled ladder tells me. So that size right there is whatever size the PCR product is. And note that this is, in the absence here, sex A1, don't get any ideas. It's from a bacterium that's S. expectatus. So first initial is the first initial of the genus name, and the next 2 are the first 2 letters in the species name, right? So sex A1. Don't provide that enzyme. That's why the minus signs, and there's no cut. So this is just to prove that all of these DNA templates produce the same sized band before digest. So what happens after I add enzyme? That's the right side of this gel. Every time there's a plus in the sex A1 line, that means I added enzyme. What happens? What's the difference between the left side and the right side? They look exactly the same. Is there a pattern? What changes, what stays the same? Do any band sizes change with the addition of enzyme? Yeah. Okay, so pick one, for example, one of the labels across the top.
CP129.
Okay, so CP129 produces, that's actually an 800 base pair product. But over here on the right side, after I add enzyme, oops, I colored over the band. It's 650 base pairs. It's a little bit smaller. So CP129 has a restriction site in the PCR product that gets cut by this enzyme SEXA1. And so I've shown you up here at the upper right-hand corner, you don't need to memorize this. Of course, you could look it up on your own if you want to, the restriction sequence for this enzyme. It's a 7 nucleotide sequence that has one of those funny nucleotides in the middle. So it's a palindrome, but it's an odd number of nucleotides, and it doesn't care if it's an A or a T in that central position. It could be one or the other, a weak nucleotide, W. But otherwise, it's a palindrome, ACCWGGT, ACCWGGT. So that's present in this strain called HK104. Here's the sequence, it's underlined, ACCA, one of the weak nucleotides, GGT. And that's why HK104, like CP129, here's HK104, 800 base pairs without enzyme, and I add enzyme, and it gets cut. We don't see the other band because it's small. So it's down here somewhere on the bottom of the gel that I'm not displaying. So why doesn't AF16, here's the AF16 sequence, the same chromosome, same region, different worm, doesn't digest in the presence of this enzyme? I add the enzyme, but its chromosome doesn't get cut. Why not?
Because it doesn't have a G at the end.
Right. It does not have that palindrome. It's ACCAGAT. So the palindrome isn't there anymore because of a point mutation that distinguishes these two strains of worms. So restrictions on enzyme digest happens in one strain, not in the other. One cuts, one does not. This is exactly the same sort of technology that geneticists around the world use after PCR to do DNA fingerprinting. Distinguish chromosomes from one source and another. And in this case, it depends entirely on the presence or absence of a single point mutation that's inside a restriction enzyme site. So we use this all the time. And you might wind up doing this in Biology 04 when you get there. So that is the end of exam 2 material. There is a practice exam. It's going to get distributed to you whenever I make myself a note to distribute it to you. And I've also created a key that's already available, and do the practice exam if you want over the weekend as a study guide. Come to class Monday, we do a review session as usual. Monday, you ask me questions, I answer to the best of my ability, and then the exam's on Wednesday. So there's a little bit more practice ability to do with these. It's not really a false exam or a mock exam. It's probably a little bit longer than the exam will be, and as you saw last time, it probably won't be quite the same difficulty. It might be harder, it might be less hard. I'm just trying to generate questions that I've written that reflect the material you should study for the exam. So it's more of a study guide than a mock exam. It's in the format of an exam. So it's a PDF, it'll get sent out to you via Google Classroom. Any questions? All right, has everybody done the Socrative activity? If not, no? Okay, good, because I need your data for the next activity. So chat with a friend for half a minute, maybe. We'll move on. Data collection has ensued. So where we're moving today is towards the next chapter, sex chromosomes. And the main reason that I talk about sex chromosomes in class, not only does it have to do with genetics and it's kind of interesting to study, is that it gives us an opportunity to start working on statistics again. So we've done a little bit of probability calculations in class so far. You've seen multiple versions of the how many times or what's the frequency of a particular DNA sequence. What's the probability of different haplotypes from the STR tables from that publication we've been working on the last couple of classes. And it's really critical for genetics, especially when we move into Mendelian genetics and we start talking about Punnett squares, to be able to do the chi-square test. It's one of the most simple statistical tests, and it's particularly relevant in genetics because of the way genetics works. So hence, for this chapter, the main tasks include statistics. So one of them is be able to predict an organism based on its karyotype. So if I show you a karyogram, if I show you a picture of chromosomes of an organism, can you tell me what sex the organism was? And then the last two tasks are more statistics-based. Predict the expected outcome of a random binary decision, like a coin flip or maybe a poker chip flip. It's a binary outcome. You flip it, it should be random, you get a heads or tails. You get a yes or no, it's a binary decision. So that's what we're going to be doing today, hence the poker chips. And then using statistics to compare that expectation. That's right, so you predict an expectation, that's what you expect to have happen, and then you observe, you do an experiment, you collect observations, you have expectations and observations. We need to know, do they match or do they not? And that's where statistics comes in. How close was your guess to what you observed? We could use a lot of qualitative language, like it's pretty close, or it's kind of close, or it's sort of close, or it's really doggone close. But as scientists, we tend to want something that's more quantitative. Like we want to be able to say, yes, are they the same, or no, are the observations and expectations different? That's why we lean on statistics to do that. Because it can turn something that's qualitatively descriptive, like it's kind of close, to something where we can make a binary yes or no, it's close or it's not. So if you'll please point your browser to this URL, either click on it if your PDF is clickable, or just type it into a browser window. You should see a little spreadsheet pop up that I've already populated with some cells. Unfortunately, this is not going to record on the recording, but you should see something like this. I think, is that what was on that URL? Okay. Does anybody need more time getting to that website? Put the URL back up.
What was the short URL?
Yep, there you go.
Thank you.
Yeah, absolutely. So I asked you all, here's the expectation. Here's where I'm going with this. You thought it was weird that I asked you in the Socratic activity which type of device you're using today, or maybe you didn't think it was weird, but I was secretly collecting data that I could use for this example. So my quick calculation was that there are 53 students in class. So all of the yellow fields you should be able to fill in. And we have to come up with, we have an observation, that is the data I collected from you. So we could type that in too. I'll tell you, you want to fill this in with me? Observed. So we had 53 students in class. And the reason I wanted to give you this spreadsheet is because you can use it. It's got some of the formulas that I used to do this calculation filled in. So if you want to go study how to type these equations and how they're used, that's fine. So 53 students in class. We need to come up with a null hypothesis, which is an expectation. Two different things. Null hypothesis sounds scary. Let's just call it an expectation. So what should we guess is our expectation for how many of you are using smartphones versus tablets versus laptops?
A third.
Sure.
Just make up a number, right? That's what you're asking.
Yeah. So we need to make a prediction, and it tends to be that when we have an expectation, that's the same thing as a null hypothesis. The concept here is that it's based on what we understand about whatever it is we're making a guess about. And so we might expect by chance that a third of the students have tablets and a third have laptops and a third have smartphones. That was my prediction. You could argue with me, you could have a different prediction if you have some numerical or observational basis for making another claim. I'm just guessing that it's going to be a third, a third, a third. So that's how the null hypothesis or the expectation gets developed. So in this case, that's how I calculated these expected numbers. So it just took the number of students in class and divided it in thirds. So are there 16 2/3 of you that are using smartphones? Does that sound stupid? I see some people smiling. What does it mean to have 16 and 2/3, or 17 and 2/3 students using a smartphone?
One student is able to divide themselves into 1/3 of them is using one device and 2/3 of them is using another.
Yikes.
I don't know about you guys, but I can do that.
So here are the actual, so those are the expected numbers. The observed numbers, based on the results from the survey, are we have 17 smartphones, 22 tablets, and 14 laptops. Like that. And the expectations then tend to be based on the number of students in class, which is 53. The number of expectations is basically 17 and 2/3 each. Now, at some point today or after the exam, the next time we start talking about this, we're going to have a discussion about why the expectation is okay to not be a biologically meaningful number. It's not a round number. Does it mean anything to have 17 and 2/3 of something being expected? We'll talk about why we don't round those numbers, even though it doesn't make sense to talk about fractions of a student or fractions of a device. So the question then we're after today is, here's a distribution of expected results, 17, 22, and 14. Is that the same as or different than our expectation? What do you think? Statistically identical or statistically different?
Different.
Right. This is pretty close, 17 and 17 and 2/3, but then tablet was more observed than expected and laptop was necessarily the opposite. So that's where we're heading. Find out if those two distributions are different. So chi-square test. I just already explained this, but since this is on the recording now, the expectation was the number of students divided by the number of categories. So this time, categories is an important idea for the chi-square test. You have to know how many different groups or categories or bins of information. In this case, we've got 3 categories that things we're measuring. How many tablets, how many smartphones, how many laptops. So we're going to use that information in a little bit. Number of categories. 3. So far we've got observations, total number of students in the class, the devices they're using, and then now we know the number of categories. And then we get to the chi-square formula. Don't freak out. It's the same thing 3 times. It's this expression, an observed number of, in this case, mobile devices, minus the expected number, square that number, divide it by the expected number. The reason that there are 3 of these, and you have to use all 3 of these clauses, you do that calculation and you add them together, is because how many categories were there? 3. There has to be one of these expressions, observed minus expected squared over expected, for every category. If you leave one of those out, you're not actually calculating the chi-squared test statistic, which is what the answer to this equation is. So in this case, one observation, I'll just fill in one of these briefly. We observed 17 smartphones. We expected 17 and 2/3, I'll just call it 17.6. And then you square that and divide it by the expected number of smartphones, which again was 17.6. So you do that for smartphones, tablets, and laptops. And that gives you this number called the chi-square test statistic. It's just a number. And that's what this spreadsheet that I sent out to everybody is doing. I already plugged in the calculation, so it automatically calculated everything. This chi-square test statistic cell has that formula, observed minus expected squared divided by expected for smartphones, and then for tablets, and then for laptops. And that gives us that value, 1.849. Now all that's left is we have to figure out what that means. This random number, 1.849, that tells us something about how similar these two categories are, expected and observed. Does anybody have any trepidation or questions they want to ask at this point? Speed up, slow down, get to the poker chips already? So when you calculate the chi-square test statistic, we're one step away from knowing if the observed and expected data are statistically or not. So we're not going to go to that step yet. Take 2 minutes. This is one of the activities that we were going to do today anyway, so let's do it. What is the chi-square test statistic, the answer to that formula for flipping a coin 4 times and always observing heads? That is, once the same side of the coin comes up 4 times in a row. Is that statistically unlikely or not? This is going to tell us the answer. So here's a hint, and I'll let you work on it. We've got expected and observed values, and what else do we need to put in a table of information to do this calculation? Right, so these expected and the observed values, the expectations and observations are either heads or tails. So if you fill that grid in, then you set up the chi-square formula. Observed minus expected squared over expected. What's the null hypothesis going to be? What do you expect? If you flip a coin 4 times, if the coin is fair, if everything's happening randomly, like distribution of laptops, smartphones, and tablets, what are our expectations? Half heads, half tails. And what's the totals going to be? The totals of the expected and the observed columns have to be the same. So how many observations were there?
4.
How many? We observed 4, so we need to have the same number of expectations. So we start with the total number of observations. That tells us the total number of expected somethings, heads or tails. And then you said you divided it in half, because half of the time, by chance, the coin should be heads, and the other half, it should turn up on the other side of the coin, tails. But we observed always heads. So out of the 4 times, it was always heads, and then thus it was never tails. So it looked like some of you were already plugging that information into that formula down in the bottom right, the chi-square formula. One clause for heads, expected versus observed, the other one for tails, expected versus observed. So for heads, that would be 4 minus 2 squared over 2. And then for tails, 0 minus 2 squared over 2. So the answer, chi-square test statistic. What is it? I've got it written down on a piece of paper up here somewhere, but I think it's a pretty, I probably could calculate it faster than I can find my answer key up here.
I got 4.
It's 4. So that's the answer to the question. The question was, what is the chi-square test statistic? It's 4. So now we're at the same place in both of our activities right now. We've got the smartphone, tablet, laptop thing. We calculated that chi-square value. We've got the chi-square value for this made-up example, flipping a coin 4 times and always seeing heads. So now we're going to figure out what we do with that information. Oh, and by the way, what's the number of categories?
2.
Heads or tails. So it's not 3, which was laptops, smartphones, and tablets. This one has number of categories equals 2. Okay, that's the reason we need that information is because we need 2 things to find out significance, statistical significance with the chi-square test. One is the chi-square test statistic value, which is the thing that's, it's chi because it's the Greek letter chi. If you say chi squared, that's fine, but I'm going to expect you to bring me some sort of hot tea-based beverage. Chi squared, doesn't really matter. I understand what you mean if you say chi squared. We need to know that number, and we need to know the number of degrees of freedom, which is a really abstract concept that I'm not even comfortable teaching because I'm not a statistician. I kind of understand what it means, but I know how to calculate it. It's the number of categories minus 1. So for the laptop example, we had 3 categories, so that would make the degrees of freedom in that case 3 minus 1 or 2. In the coin flip, we had 2 categories minus 1 gives us 1 degree of freedom. So with the numbers of degrees of freedom and the chi-square value, we're now armed to figure out probability or p-value. That's the thing that we have to know that tells us whether or not the numbers are significantly different. Normally to do this, there are 2 ways to do this analysis. To go from chi-square value and degrees of freedom to p, the probability. You can use this table or you can use Google Sheets or Excel. So I've plugged the formula in to that Excel spreadsheet that you have access to. You can look it up if you want to. We'll talk about it later next week. In the meantime, for our coin flip, what was the chi-square value? 4. So here's how you use this table if you haven't done this before. The column on the left here says degrees of freedom. 1, 2, 3, 4, 5, 6, 7, 8. Find the row that has the degrees of freedom that you've got. In the coin flip when it's 1. 2, heads or tails, minus 1 was 1 degree of freedom. So we're looking in this row. And in this row are chi-square values. So we're looking for where we see 4, the chi-square value we calculated for this. So where's 4? It's somewhere in between 3.8 and whatever that says, 6.6. So it's in that range. That's all we want to know. We want to know the range. You will rarely, if ever, actually find your chi-square value in this table. It's a table of ranges. So in that range is our test statistic, 4. The last thing you do, this is the key, is you look up in this header that says p-values. And you find out the range of p-values, circle in yellow, or whatever color that is, green, chose the wrong color, the range of p-values that flank your chi-square value. So chi-square value 4 has a p-value somewhere between 0.05 and 0.01. Right, our 4 is somewhere in between those 2 numbers, so its p-value is somewhere between those 2 numbers in the header, the top row, between 0.05 and 0.01. That's our p-value. If I was writing, p is between 0.05 and 0.01. So some questions, when we get there, some questions will ask you what's the p-value. That's what you would report as a range. If you use Google Sheets or Excel, you can calculate an exact p-value, not a range. Either one would be acceptable. So the last thing we need to figure out how to do is what that p-value means. This is the last step. Calculate chi-square, degrees of freedom, look up the associated p-value. Now we have to interpret the p-value. The p-value is what tells us is it statistically significant or not. In the coin flip example, it's what happens if we don't see what we expect? What does it mean in real life if you're at a casino and you flip a coin 4 times to win money and each time it comes up heads?
The null hypothesis is invalid.
So what that's the scientific version means the null hypothesis, our expectation was wrong. We expected 2 and 2, but every time we flip the coin, what does that mean to us if we go gambling? What's going to happen if we keep flipping the coin and it keeps turning up heads over and over and over again? You might not be, I don't gamble, you might not be gamblers either, but guess what happens?
It's good.
Somebody accuses the casino of using a weighted coin, right? It's an unfair game. Right? That's what this test is meant to identify. Are the results significantly different than what we expect? P-value, here it is. You've heard it before, probably. P-value less than 0.05, less than or equal to 0.05. Means that there's a significant difference between the two sets of data. In other words, the p-value we just looked up was between 0.05 and 0.01, which is smaller than 0.05, which means that if you flip a coin in 4 times and you get the same result every time, that's not random. That suggests that there's a significant difference between 2 and 2, the expectation, and the observation, 0 plus 4. 0 tails, 4 heads, for example. And this 0.05 number that scientists use is just, it's an arbitrarily chosen number. Somebody had to pick a number and said, there's this p-value, or probability, and we just are going to say that if it's smaller than 0.05, that we're going to say that the results were statistically significantly different. So in this case, because our p-value is less than 0.05, we would go up to the casino manager and accuse them of fraud. You're using unfair coins. If the p-value is bigger than 0.05, it can range from 1 to 0, p. So that's the range of probabilities, 1 to 0. So if p is greater than 0.05, that means the results are not statistically different. You can't distinguish them from chance. And before we get there, let's quickly look at our analysis of data from today. So I'd already, as I said, set up this spreadsheet to calculate p for us. So in this case, what's p? P was 0.039. So what's the interpretation? Statistically similar or statistically different, the observed and the expected values? Similar. P of greater than 0.05 means the observed and the expected values are basically indistinguishable from each other. It's only if p is less than 0.05 that you'd say they were different. So the observed and the expected values are statistically similar. In other words, what we would say in science, which is horrible, the null hypothesis is supported. Null hypothesis, expectation. Our expectations are true, they're supported. If p is less than 0.05, we'd say something like the null hypothesis is rejected. Rejected, yeah. Yeah, we don't like it. All right. So in the last 5 minutes, to create some data to work on for next class, to do a little bit more chi-square practice, let's use those poker chips. So on Google Classroom right now, once you're done taking notes or doing whatever it is you're doing, if you go on Google Classroom, there's a new exercise that's been released that looks something like this. It's called coin flip chi-square, if you're not finding it. But it's out on Google Classroom right now. And what I'd like you to do is to go into this spreadsheet, read the instructions, but here's the thing to do. Each of you get access to the same spreadsheet. That is, we're all going to be working on this all at the same time. So there are two important things before you get started working on this. One is, the first thing to do, pick a row and put your name in column A. Please don't type over somebody else's name. This is the tricky part, because everyone's going to be picking a row at the same time. So pick a row, put your name in it, and then we're going to do the second step. We're going to try not to crash Google Sheets. Once you've done that, type this formula into column B next to your name, the one that says number of coin flips, random. What I'm asking you to do is what this is doing is it's letting Google Sheets randomly generate a number of times you're going to flip your poker chip. And so this equals rand between parentheses 1, comma 10, end parentheses, is the random number generator formula that you tell it, pick me a random number between 1 and 10. As soon as you do this, this is the part you need to know before you do this. As soon as you type that into that cell and hit enter, or the check mark, it's going to put a random number, a whole number between 1 and 10 in that cell. Remember what that is immediately, and type that into the cell next to it, the one that says record. You're recording whatever that formula spit out for you. Whatever number it was in cell B, type that number again in cell C. That's because every time somebody hits enter anywhere on this spreadsheet, this random number generator is going to generate you a new random number, which is not useful. So whichever one is the first random number you get, just type that in there. In column C. And when you're done with that, go ahead and make your observations. Flip the number of times Google Sheets has asked you to, and record your observations in the yellow number of bicycles or heads, I guess, and number of spades or tails. Bless you. And again. If you have any technical support questions, please raise your hand.